Hey everyone, ready for another deep dive? Today we're looking at Python for numerical methods.
Sounds fun.
It is.
Yeah.
And I think our listeners are really going to enjoy this one. They're going to want to know, well, the why, the how, and all those numerical calculations, right?
Right.
We've got some interesting stuff here. Python can help us find, did you know this? It can help us find the roots of equations
Oh, yeah.
and even figure out those definite integrals.
Yeah, it's a pretty amazing tool. I use it all the time for those kinds of problems.
Yeah.
Yeah.
Cool. So let's get into it. The stuff we have here, it starts off with, a little intro to Python, like a crash course,
Yeah.
And it talks about how readable Python is and how you can easily maintain it, keep the code clean.
Yeah.
And that seems really important for numerical methods.
Absolutely. Absolutely. When you're working with all that complex math, it can get really messy really fast. Having clean, organized code it's just crucial. For accuracy, for everything, makes it a lot easier to find and fix errors, too.
Makes sense. I'm also seeing here, talks about libraries.
Yeah.
And the availability of source code.
Oh, yeah, that's huge. Having access to those pre-built functions and all those open source resources, it saves us a ton of time.
Yeah.
We don't have to reinvent the wheel every single time, you know? It's like we've got this massive toolbox full of specialized tools just ready to use.
Oh, that's a good analogy.
Right.
So have you ever used Python before?
Oh, yeah, tons. It's my go-to for pretty much all my numerical work.
Really?
Oh, yeah.
Cool. Well, this next section we're going to dive into, it talks about linear algebra with NumPy. It's like the basis of so many of those numerical calculations.
It really is. Linear algebra it's fundamental. And NumPy, it just makes working with vectors and matrices in Python, it makes it, almost effortless.
Right. And the material talks about how NumPy is used for, all those different calculations.
Exactly. It's super efficient for things like integration, finding derivatives, interpolation, and even signal processing. You name it. It handles all the heavy lifting so you can focus on the analysis, not getting bogged down in all those tedious calculations.
That makes a lot of sense.
Yeah.
There's even a little code snippet here showing how to make vectors and matrices using NumPy. It actually looks pretty easy.
It is. NumPy takes care of all the complexity behind the scenes, so it's really user-friendly.
Okay, now for something that sounds kind of intimidating at first, root finding methods. Have you ever tried to find the root of an equation?
Oh, sure. Finding roots, it's like solving an equation, figuring out what value for the variable makes the equation true. It's really important in a lot of fields.
Yeah.
Physics, finance, you name it. Helps us model and understand different phenomena.
It's like solving a puzzle, isn't it?
It is.
You're trying to find that missing piece.
Exactly.
Well, the source material uses this thing called the bisection method as an example.
Right.
It really breaks the whole process down step by step, which I think is great. You're essentially, narrowing down that interval where the root lies until you get close enough.
Yeah, the bisection method, it's a great starting point. It's relatively simple, and you're guaranteed to find a root. Well, as long as certain conditions are met, of course. But there are other methods like Newton-Raphson and the CCAT method, which might be faster, but they're not always as reliable.
Oh, interesting. So it's like choosing the right tool for the job based on the equation you're working with.
Exactly. Sometimes the simplest method is all you need. Other times, a faster method might be better, even if it's a bit riskier.
Can you imagine how finding roots might be useful in your own work? It seems like something that pops up in a lot of different areas.
Oh, absolutely. Imagine calculating interest rates or predicting the trajectory of something like a rocket, or even designing a video game.
Wow.
It's all about finding solutions to equations, and those root-finding methods, they're the tools that help us do that.
Okay, let's shift gears a bit. Let's talk about interpolation. Ever needed to, estimate a value between two data points? That's where interpolation comes in. It's like connecting the dots.
Exactly. You're finding a function that fits those data points, and then you can use that function to estimate values at points within that range.
The material talks about Lagrange interpolation, building a polynomial, that goes through all those data points.
Yeah, Lagrange interpolation is really useful when you need a perfect fit, especially if you don't have a ton of data points.
It's like drawing a smooth curve that goes through all those points on a graph.
Exactly. And of course, if you've got a lot of data points, things can get a bit messy.
Yeah.
That's when other interpolation methods might be a better fit.
So the choice, like with those root-finding methods, depends on what you're working with.
Absolutely. There's no one-size-fits-all in numerical methods.
That's a good point.
It's about choosing the right tool for the task.
Okay, ready for a big one? Numerical integration. This lets us handle those tricky, definite integrals, especially when, finding a regular solution is just too hard.
It's incredibly useful. Think about physics, engineering, economics, you name it. You often need to figure out the area under a curve, right?
Yeah.
And sometimes you just can't solve the integral directly. That's where numerical integration comes in. It gives us a way to approximate that area even when things get really complex.
The material uses this thing called the trapezoidal rule.
Yeah.
As an example. It seems pretty smart, actually, dividing the area under the curve into a bunch of trapezoids.
The trapezoidal rule is a great starting point. It's all about breaking that complex problem down into smaller, easier pieces, like a lot of numerical methods. And of course, there are more accurate methods like Simpson's rule or Simpson's 38 rule. They use different shapes to approximate that area.
It's amazing how these methods provide solutions when regular calculus, just hits a wall. I'm really starting to see just how powerful these numerical methods are.
They really are essential, especially for dealing with those real-world problems.
Okay, now let's step into the world of ODEs. Ordinary differential equations. I know they sound kind of intimidating, but they're actually key to understanding how systems change over time.
Yeah, ODEs describe the relationship between a function and its derivatives. Think about the flow of current in an electrical circuit, or the motion of a pendulum, the way it swings back and forth, or even how a disease spreads.
Wow.
All of these things, they're dynamic systems, and ODEs are what we use to model them.
So it's like using math to capture how things evolve over time.
Exactly. And, there are different types of ODEs, linear, nonlinear, initial value problems, boundary value problems. Each of these requires its own specific approaches.
The material focuses on Euler's method. It's, like a basic technique for solving ODEs.
Yeah, Euler's method is a good one to start with. It uses the value at a previous time point and the rate of change to estimate the value at the next time point.
It's like using the information you have now to predict what will happen next. Interesting.
It's a first-order method, meaning it uses a linear approximation. It's simple, easy to understand, but it can be a bit less accurate, especially when the solution is changing rapidly.
Oh, I see. So like with other methods, there's that balance between simplicity and accuracy.
Right. And for better accuracy, well, there are more sophisticated methods like the modified Euler method or the Runge-Kutta methods.
The material mentions those, but doesn't really dive in too deep.
Yeah.
Maybe we'll have to do another deep dive on those sometime.
Yeah, maybe.
Okay, last topic for this part of our deep dive. Optimization. This one's pretty relatable, right?
Yeah.
We're always trying to find the best way to do something, the most efficient solution, right?
Optimization is, it's all about finding the best solution, finding the values of variables that minimize or maximize a certain function. And often we have to do that within certain limits or restrictions. It's used everywhere. Engineering, finance, machine learning.
And just like with those ODEs, there are different types of optimization problems, right?
Oh, absolutely. We have linear and nonlinear problems with constraints, and those without, and so many different techniques for tackling each type.
The material talks about gradient descent. It's a pretty popular technique, especially in machine learning, it seems.
Gradient descent is really cool. It's an algorithm that starts with a guess, and then it keeps updating that guess by moving in the direction of the steepest descent. Imagine you're on a hillside and you want to find the lowest point. You walk downhill.
Yeah.
That's essentially what gradient descent does. It's relatively simple to implement, and it can handle those really large, complex problems.
It's like you have a compass that's always pointing downhill. It guides you right to that best solution.
That's a great analogy.
But even gradient descent has its challenges, right?
Right. Sometimes it can get stuck in a local minimum, a point that's lower than its neighbors, but not necessarily the lowest point overall.
It's like thinking you've reached the bottom of a valley, but there's an even deeper valley hidden just over the next hill.
Exactly. And that's why there are all these different techniques to help gradient descent avoid those local minima.
It's fascinating. I'm seeing the material also mentions a few other optimization techniques, like simulated annealing and particle swarm optimization. It seems like a whole toolbox of methods for finding those best solutions.
There are a lot of different approaches, for sure, and choosing the right one often depends on the specific problem you're dealing with.
This is already a lot to take in. We've covered Python basics, linear algebra, root finding, interpolation, integration, ODEs, and even optimization. Phew. Let's take a break here, and we'll dive into these fascinating concepts a bit deeper in the next part of our exploration.
Sounds good. It really is amazing, you know? All these numerical methods, they're so diverse, but they all have this common thread, breaking down those complex problems into smaller steps, steps that computers can handle.
It's like we're speaking a secret language,
They're like,
a language that lets us talk to computers and get them to solve problems that, well, problems that would just be way too hard for us to do on our own.
exactly. And the best part, these tools, they're constantly evolving, getting more powerful, more accessible. It's really exciting.
So from everything we've talked about so far, from those Python basics all the way to optimization, what really stands out to you? What's sticking in your mind?
I think it's how connected everything is,
Yeah.
how a solid understanding of linear algebra, it's essential for working with those libraries like NumPy. And then those libraries, they form the foundation for so many of those calculations. And those calculations, well, they're key for solving those ODEs, doing integration, finding roots, optimizing systems. It's like this beautiful web of math all working together.
That's a great point. It's not just a bunch of random techniques. It's a framework for problem solving. But let's bring it back to our listeners for a second. Why should they care about all this, even if they're not, mathematicians or programmers? How could this knowledge be relevant to their lives?
That's a great question. The truth is, these numerical methods, they're everywhere, even if we don't see them. They're used to design the products we use every day. They're used to model financial markets, predict the weather, analyze data. Even just a basic understanding of these methods can give you a deeper appreciation for how things work, how problems are solved in all sorts of fields.
I love that. It's like peeking behind the curtain, seeing the machinery that makes everything run. The material actually goes a bit deeper into the importance of those libraries and the availability of source code. Why is that so crucial for numerical methods in Python?
Python's real strength is in its libraries, especially for numerical stuff. Libraries like NumPy, SciPy, Matplotlib, they're essential. NumPy is our go-to for handling arrays and matrices. SciPy gives us this treasure trove of algorithms. And Matplotlib, well, that lets us visualize our data, see what's going on. And the best part, these libraries, they're open source. They're free, constantly being improved, and available to anyone.
It's like this huge collaborative effort, people from all over the world working together to make these tools better.
Exactly. And that's a big reason why Python is so popular for this kind of work. It's a vibrant community, constantly pushing the limits of what's possible.
Now, I stumbled upon something interesting in the material about the bisection method. It mentions this idea of robustness. What does that mean in this context?
Robustness, it basically means how well a method can handle variations or uncertainties in the data you feed it. With the bisection method, it means that as long as those initial conditions are met, it's guaranteed to find a root. Even if the function is a bit messy or doesn't behave perfectly.
So it's like a dependable friend, always comes through, even when things get tough.
Exactly. In the real world, our data is often noisy, inaccurate. So having those robust methods that can handle those imperfections, it's really valuable.
Speaking of different methods, the material mentions Lagrange interpolation. It's a good choice when you need that exact fit to your data points, especially if you only have a few. Why is that?
Lagrange interpolation, it builds a polynomial that passes through all those data points. It's like drawing that smooth curve that connects all the dots on a graph. But as you get more and more points, the polynomial can get pretty complex. And that can lead to some weird oscillations, especially if your data is a bit noisy. So for larger data sets, you might want to consider other methods that give you a smoother fit.
It's like trying to thread a stiff piece of string through a bunch of scattered points. With a few points, it's easy. But with more points, you end up with a tangled mess.
That's a great way to picture it. It's important to remember that in numerical methods, there's often this trade-off between accuracy and complexity. Sometimes a simple method is enough. Other times, you need a more sophisticated approach, something that captures all those nuances in the data.
And the material mentions Newton's divided difference interpolation as an alternative to Lagrange. What are the advantages of using Newton's method?
One big advantage is computational efficiency, especially when you need to, add or remove data points. With Newton's method, you can update the interpolation polynomial without having to recalculate everything from scratch. That can save a lot of time, especially with those big data sets.
So it's like having a system that can adapt to changes instead of having to rebuild everything every time something changes.
Exactly. In real-world applications, data is constantly being updated. So having methods that can handle that, well, it's really important.
Let's move on to numerical integration. The material talks about a bunch of different methods. Trapezoidal rule, Simpson's 38 rule, even Gaussian quadrature. Can you give us a quick rundown of how these methods differ and when you might choose one over the others?
Sure. Think of them as different tools for approximating the area under a curve. Trapezoidal rule uses trapezoids, Simpson's rules use parabolas, and Gaussian quadrature uses this weighted sum of function values at specific points. Each method has its own accuracy and computational cost. The choice depends on a few things, like the accuracy you need, the complexity of the function, and the computational resources you have.
So it's like having a set of measuring tools, each with different levels of precision. You wouldn't use a ruler to measure the distance between two cities, just like you wouldn't use a really complex integration method for a simple function.
Exactly. It's all about using the right tool for the job. And, numerical integration, it's incredibly important in all sorts of fields.
Can you give us some examples of how it's used in the real world?
Absolutely. In physics, you might use it to calculate things like work or energy. In engineering, it helps you analyze things like stress and strain in materials. In economics, you might use it to estimate consumer surplus. There are tons of examples.
It's like having a powerful lens, one that lets us see and measure things that were previously hidden.
That's a great way to put it. Numerical methods, they often give us the ability to understand these complex systems, to analyze them in ways we couldn't before.
Now let's get back to those ODEs for a moment. We briefly touched on the difference between linear and nonlinear ODEs. Can you explain why that difference is so important?
The difference is all about the relationship between the function and its derivatives. Linear ODEs, they have these simple linear relationships. But nonlinear ODEs, they can have much more complex, more intricate relationships. And this difference, it's crucial because linear ODEs often have those nice, neat analytical solutions. But nonlinear ODEs, well, they rarely do. And that's where numerical methods really shine. They allow us to solve those nonlinear ODEs.
So it's like having a clear roadmap versus trying to navigate a dense jungle. Linear ODEs, they're like those well-marked roads. Nonlinear ODEs, they're like uncharted territory. You need different tools and techniques to explore them.
That's a fantastic analogy. That linear structure of linear ODEs, it makes them more predictable, easier to solve. But the nonlinear ODEs, well, their behavior can be unpredictable, complex. So we have to rely on those numerical methods to find those solutions.
The material also distinguishes between initial value problems and boundary value problems, when talking about ODEs. Can you explain those concepts a bit more?
Of course. Initial value problems, they give you information about the function and its derivatives at a single point, usually the starting time or location. Think about it like knowing the initial position and velocity of a ball you throw into the air. Boundary value problems, they give you conditions at multiple points, often at the boundaries of the system, like knowing where the ball starts and where it lands, but not necessarily the path it takes in between.
So it's like having different types of clues to solve a puzzle. Initial value problems give you that starting point. Boundary value problems, they give you constraints at different points.
Exactly. And the type of problem, it determines which numerical methods you use to find those solutions.
We talked about Euler's method as a basic technique for solving ODEs. The material mentions it's a first-order method. Can you remind us what that means?
A first-order method means the approximation at each step only depends on the value at the previous step. It uses that linear approximation based on the slope at that previous point. It's easy to implement, but it can be less accurate, especially when the solution changes rapidly.
It's like taking small steps, relying only on the direction you're facing at each step. If the path is straight, it's fine. But if it's curvy, unpredictable, you might end up way off course.
That's right. And that's why we have those higher order methods like modified Euler or the Runge-Kutta methods. They use more information to improve the accuracy.
The material mentions those higher order methods, but doesn't really go into detail. Can you give us some more insight into how they work? What advantages do they offer?
The modified Euler method, it's a second-order method. It uses the average of the slopes at the beginning and end of the interval to improve the accuracy. Runge-Kutta methods, they're a whole family of methods that use multiple stages to estimate the slope. That gives you even higher accuracy. The most common one is the fourth-order method, usually called RK4. They're a bit more complex to implement, but they offer a big improvement in accuracy.
So it's like having a more advanced navigation system, one that considers the curvature of the path and makes adjustments for a smoother, more accurate journey.
Precisely. They use more information about the solution to get that better approximation.
Okay, let's shift back to optimization. Remember those terms: objective functions, Decision variables, constraints. Can you break those down for us again?
Sure. The objective function, that's what you're trying to minimize or maximize. It represents your goal. Like if you're trying to minimize cost, the cost function is your objective function. Decision variables, those are the things you can adjust, the choices you can make to influence that objective function. And constraints, they're the restrictions on those decision variables, the limitations you have to work within.
So imagine we're planning a road trip. The objective is to reach our destination. The decision variables are the route we take, how fast we drive, and the constraints are things like speed limits, how much gas our car holds, and maybe road closures.
That's a great analogy. It really shows how optimization is about making the best choices within those limitations to achieve your goal.
The material mentions a few different types of optimization problems: constrained and unconstrained, linear and nonlinear, deterministic and stochastic. What are the key differences between them?
Constrained optimization problems, they have limits on those decision variables. Unconstrained problems don't. Think about finding the highest peak in a mountain range. That's unconstrained. But finding the highest peak within a fenced-off area, that's constrained. Linear programming problems, they have linear objective functions and constraints. Nonlinear programming, well, it involves those more complex nonlinear relationships. Deterministic optimization, it assumes you know all the parameters. But stochastic optimization, it incorporates uncertainty, randomness into those parameters.
Optimization comes in so many forms, each with its own challenges and ways to find solutions. It's fascinating.
It really is. And the technique you choose often depends on the specific problem you're trying to solve.
We talked about gradient descent as a popular technique. Can you remind us how it works?
Gradient descent, it's an iterative algorithm. Starts with an initial guess. Then it repeatedly updates that guess by moving in the direction of the negative gradient towards the steepest descent. Imagine standing on a hillside, wanting to find the lowest point. You would walk downhill, right? That's essentially gradient descent. It's relatively simple and can handle those large-scale problems.
It's like having that compass that always points downhill, guiding you to the best solution.
Exactly. And the beauty of gradient descent is that you can apply it to a wide range of problems, from simple linear models to those complex neural networks.
The material mentions some challenges with gradient descent, like getting stuck in those local minima.
Right. A local minimum, it's a point where the function is lower than its neighbors, but it might not be the lowest overall. Gradient descent can get trapped there if the initial guess is too far from the global minimum, or if that learning rate isn't set right.
It's like thinking you've reached the bottom of the valley, but there's an even deeper valley hidden just over the next hill.
Exactly. And there are techniques to help gradient descent escape those local minima.
Well, I think we've reached a good stopping point for now. We've explored how all these numerical methods are connected, looked at the nuances of different techniques, and started to see how these tools are used in different fields. Let's take a break, and we'll wrap up our exploration of Python for numerical methods and optimization in the final part of our deep dive. Welcome back, everyone. You know, I'm still thinking about all those insights we talked about. Numerical methods are really the unsung heroes, aren't they?
They really are. Working behind the scenes, making things happen.
Yeah.
From the tech we use every day to those big scientific discoveries.
Absolutely. And speaking of pushing those boundaries, I found something interesting in the material. It talks about least squares fitting. You know, when you're fitting a curve to your data.
Yeah.
It's different from interpolation, where you try to make the curve go through every single point.
Right. With least squares, you're not going for a perfect fit through all the points. You're trying to find that curve that minimizes the overall distance between the curve and all those data points.
Oh, I see.
It's really useful when you're working with noisy data or data that has those outliers, those points that are way off from the general trend.
So it's like you're finding the best overall fit, the one that really captures the trend, rather than getting hung up on those individual points that might not be that accurate anyway?
Exactly. Least squares fitting is a fundamental technique really important in data analysis and modeling. It helps us extract those meaningful insights, even when the data's a bit messy.
And there are different types of least squares fitting, right? The material mentions linear and nonlinear.
Yeah, you choose the method based on the relationship between the data and the model you're trying to fit. If it's a linear relationship, you use linear least squares. But if it's more complex, involving curves or nonlinear functions, then you go for nonlinear least squares.
It's like having those different tools for different jobs, right?
Exactly.
You wouldn't use a hammer to screw in a screw, right?
Yeah.
Just like you wouldn't use linear least squares to fit a complex nonlinear model. You got to use the right tool for the job.
I like that. It's all about understanding those methods, their strengths, their weaknesses, and choosing the best one for the situation.
So as we wrap up this deep dive into Python for numerical methods and optimization,
Yeah.
what are your thoughts on the, I don't know, the big picture? Anything you're particularly excited about? Any emerging trends?
One thing that really excites me is how numerical methods, optimization, and machine learning, they're all coming together.
Oh, yeah.
Machine learning relies heavily on optimization, to train those models, find those best parameters. And as machine learning keeps advancing, I think we're going to see even more sophisticated optimization algorithms specifically designed for those machine learning challenges.
Wow. That's interesting.
Another area I find fascinating is the development of numerical methods and optimization for, get this, for quantum computing.
Quantum compute.
Quantum computers have the potential to revolutionize things. Scientific computing, optimization, all sorts of fields. It's still early days, but it's incredibly promising.
It's mind-blowing to think about the possibilities, isn't it? It feels like we're on the verge of some major breakthroughs, all thanks to these incredible tools and techniques.
I think so, too. It's a really exciting time to be working in this field.
Well, that brings us to the end of our deep dive into Python for numerical methods and optimization. It's been a fantastic journey exploring all this with you.
I've really enjoyed it. Thanks for having me.
And a huge thank you to you, our listener, for joining us. We encourage you to keep exploring, keep learning. There's a whole world of knowledge out there just waiting to be discovered. Until next time, keep that curiosity burning.